Thanks, Betsy, very much for putting this together and for inviting me. It's a very good program. I'd like to tell you a little bit about climate change and land use. I was asked to mention about that too, and water quality. One of the problems that we've been hearing about today is that climate change is, of course, caused by greenhouse gases. And I've been taking students to meetings ever since 1992 Rio Earth Summit. So for more than 20 years, going to meetings, all trying to argue about how to reduce this curve, level it off, and begin to turn it upside down. And for 20-some years, we've been pretty unsuccessful, as you can see from the rising tide here. But that's the national, it's the Iowa, it's the national, and it's the global challenge, I guess, is to first level it off. We haven't even been able to do that. And then turn the curve upside down such that it would go off, this doesn't show up very well, but that it would go off the chart, maybe down to about 10 gigatons of carbon dioxide equivalents per year from perhaps 50. That's about an 80% decrease in emissions that we need by 2050. So it's a pretty tall order, and we haven't begun to really embrace it yet. That results in, of course, carbon dioxide concentration in the atmosphere now about 400 parts per million in the upper corner of this, and those are, in fact, radiatively important trace gases. We know that when you shine infrared radiation coming off of the Earth onto these gases, that they both vibrate and rotate, and that is the global, the greenhouse effect in which they trap the energy like a blanket and cause the Earth to be warmer. Iowa, as I think several have said, and Jerry Hatfield too, we're somewhere in the average, something like about 0.8 degrees Celsius. That's about 1.4 degree Fahrenheit warmer in the past 100 years. But you can see other places are much, much warmer than Iowa. Actually, we're fortunate. You could say if you lived in Siberia that you might enjoy a 2 degrees Celsius increase in temperature already. But certainly the Arctic, which isn't fully shown here, and even the oceans, notice, are much, much warmer. We're storing more energy in the oceans each year than 20 times more than all the primary energy consumption in the world. That's the legacy that we're leaving for future generations. So I think it's lost on the public that there's so much energy being absorbed by the planet, and we measure it very well. We have 3,000 sondes in the ocean called Argo floats. You can look them up on your computer and you can see where they're floating at any time. We measure very precisely the amount of energy coming into the oceans and very precisely all the energy going out, and we know for a fact that it is warming. And it's a lot of heat when you consider it on a year-by-year basis. So it kind of leads me to conclude that we really do have to address this problem, because otherwise the imbalance, the increased warming, just goes on and on and on. Of course, the more local phenomenon has been talked about here today, and that is that if you look in our meteorological records for Iowa, generally spanning 100 years or more, the clearest thing in those records, bar none, and it's highly statistically significant, is that we're receiving more intense precipitation. The 1 percentile most intense events, typically, let's say, more than 4 inches of rain in a year, are occurring much, much more frequently. In fact, and I've done this, if you look back in our records, say here in Iowa City, back to 1900, say, you're hard-pressed to find any days where it rains 4 inches in a single day. But now it's not uncommon at all. We've had one event already this spring, April 17th. Last spring we had, I think, 6 inches in Solon. So not a big change is that we're getting these events much, much more frequently. It's got implications and impacts associated with water quality too, as you can imagine. So this was not too far from here in Oakville, Iowa, when the levee broke in 2008. It looked like this. And we think we're beginning to understand why these more intense storms occur. We have real good evidence from satellites that with infrared instruments that the moisture in the atmosphere is increasing. It's also highly statistically significant. And in fact, very high clouds seem to contribute to these really intense precipitation events. Of course, this is my office in the Center for Global and Regional Environmental Research is right here, and we were flooded in 2008, almost flooded again in 2010, or in 2012. And this is Cedar Rapids, of course, in 2008, the entire downtown, as Wanda mentioned, billions of dollars of damage, and truly, we're still not back yet. So I think we're going to have to come to grips with this problem. Again, on the more local level, if you ask, well, what have been the changes in this 100-year record? This is data from Gene Tockley at Iowa State, whom we work closely with. You can see that in 1896, that's where the record goes back to, we had about 27 inches of precipitation per year, and more recently, about 36 maybe inches of precipitation a year. That may not sound like too much, from 27 to 36, but what matters is when are the events that are difficult to cope with from a standpoint, yes, of public health, and from a standpoint of flooding, and even from a standpoint of water quality. In Iowa, when we get more than, let's say, 4 inches in a day, that's one clue, but also on annual, this is annual precipitation here, if you get more than 40 inches in a year, you're kind of in trouble in dealing with it. So we can sort of think of the record in two pieces, maybe, if you will. Down the middle of the first 50 years here, you see we had maybe 1 year greater than 40 inches of precipitation to deal with. And the last 50 years, there were 1, 2, 3, 4, 5, I don't know if that's 1, 6, 7, 8, 9, 10 times. So it's really not so much the difference between 27 inches of precipitation a year and 36, but rather the difference between maybe 1 year that you have to worry about extreme flooding and 10 years, a 10 to 1 ratio. That's the notion of the extremes that we're talking about and why it's so important. And the same can be said for water quality. As mentioned by Jerry Hatfield, soil loss is one that occurs in these intense precipitation events, particularly if it's in the spring and the crop hasn't canopied over yet. We're looking at large soil losses. And for years, we've probably been underestimating how much soil we actually lose because it's difficult to account for these extreme events. In addition to being a sustainability and a soil erosion problem, this is a water quality problem, of course, too, because some of that sediment, soil, is delivered as suspended sediment into the streams, covering up habitat for fish, turning the water turbid, causing increases in water treatment costs for cities and municipalities. I was asked to talk a little bit about land cover. One of the complicating factors as scientists is that we have to try to often extract the signal in these changes of hydrology and water quality due to changes in land use from those due to climate. And sometimes they have somewhat similar effects. This is the land cover map for Iowa. I think this is the 2002 version. And of course, the dark kind of grayish is row crop agriculture, corn and beans. And you can see that a large fraction of Iowa is indeed in those two crops mentioned by Jerry earlier, the corn and beans. And that has changed a little bit in recent years. There's been basically a switch towards more corn as a result of the corn ethanol industry. And so that changes the land use a little bit, and we try to extract that information. Right now, we use models to do that. The soil water assessment tool so-called SWOT is one that we're using here at the University of Iowa, and we're running the Iowa Cedar River Basin. Here's the basin and all the stations. We have 8 different stations in which we have high-frequency data on water quality and flow rate. And you can see in this scenario, in this land use depiction, that mostly we're in corn and other row crops, which is beans in the Iowa Cedar River Basin. And this is in work in cooperation with Iowa State University, and one of my students, Lance Lee, and it's kind of hot off the presses, and I thought I'd show it to you today. Basically, we tried to take these real-time sensors in the basin and connect it with all kinds of third-party data, including satellite data, NextRad radar data, and all the data sources, digital elevation maps, land use, and we put it all together in a model that runs in real time with the eventual hope of being able to make warning and engineering judgments about perhaps agricultural decisions, and also maybe to warn downstream water users like a water treatment plant that there could be problems for treatment in the future. And I won't spend a long time on, there's new high-powered tools for calibrating and validating these models. We're in a big data environment now, and when you have a really data-rich environment, the tools become much more powerful, I think, in actually making projections for the future. So we have a large amount of data in which we can calibrate the model. This shows the green is the 95%, The green is the 95% confidence intervals. The blue are the observations. We'd like the green to overlap with the blue everywhere. It doesn't always. You can see one there, or a peak that we missed, a little bit of a peak that we missed. But in general, this is a total of 20 years or so of data, and you can see that we think we have the model simulating the observations quite well. Then we withhold data. This is about 8 years of data withheld, and we use the same parameters to try to reproduce the historical data, and you can see this is for the flow rate, the stream flow at Wapello, at below Columbus Junction, where the Iowa and Cedar come together. So we're looking at the flow rate at that exit point right now, and pretty good agreement, I think you'd agree, between observations and the model results. Well, then we can, now that we have a validated model with historical data more than 20 years, now we can try to make climate projections. But to do that, you have to know what the climate is in the future. And about the only thing we can do are to use many of the climate simulations that Professor Stanier was talking about in the first session today. We take regional climate models, smaller scale, and embed them in global climate models, general circulation models. We're doing 11 of them currently that together with Bill Gutowski at Iowa State University. They're the colored, these are called box and whisker plots, the colored statistics for December, January, February, March, April, May quarter, June, July, August, that critical summertime when the corn is pollinating that Dr. Hatfield was mentioning, and last September, October, November for, here's the period, 27 years with 11 different regional climate models and GCM. And this is unpublished, but I thought you'd find it interesting. The points beyond the box and whisker are the extremes that we were worried about earlier. And basically what it shows is that the observations are in white and the calibrated model is in gray. And you can see that we have a pretty good representation of, from the general circulation models of the contemporary climate, as we call it. So now we think that we can use the regional climate models and the general circulation models to predict the future, because we can predict the recent contemporary climate. And when we do that, I don't know if you can see it, but so this is the statistics for each quarter, the 11 climate models and the observations and the calibration of the model for winter, spring, summer, fall. And if you go, I need to get a better representation of this, I'm working on it now. But if you go back and forth, this is historical, this is projected for 2041 to 2068. I think you can see that basically all of the quarters, the winter, the spring, and the fall get much wetter, and with some increase in extreme values as well. But the summer, as Jerry Hatfield said, stays about the same or even gets drier in some of the representations. So in a nutshell, what we're saying here is that based on all of this data, we expect Iowa to get warmer, yes, but wetter. Wetter especially throughout the year, but not the summer. So punctuated by drought. Warmer and wetter, intense events punctuated by drought, especially in the summer. And that's where we think we're going. Now that has one of the things we've done that not too many people have done is we've tried to extend this to water quality also, which was supposed to be my topic, and I should summarize that. For nitrate, it looks like because it's warmer, there's more denitrification, Jerry, and we get actually improvements in nitrate in the future climate scenarios. But for runoff, it gets much worse. More events, more worries about flooding and so on. For sediment, it also gets worse because of the increase in soil erosion. So that's kind of what we're seeing, at least with the current models. And just a few last points. You know that climate is already changing. It's changing in Iowa as well. And the clearest thing in our record is this increase in more intense precipitation events. The climate models indicates that those trends will continue, but punctuated by periodic drought, especially in the summertime. Both, I didn't have time to tell you all the story, but both land use and climate change play a role. The good news is that when we change climate change to pay farmers to put more land into riparian buffer strips, more wetlands, and greater stream margins in forests, we do see improvements in water quality. But of course, this would require pretty good transfer payments and some national resolve that we're going to do that. I like to tell my students that, you know, I was going to school at the University of Texas in 1972, and I remember we passed the Clean Water Act. And we spent more than $100 billion as a nation because we were resolved to improve the water quality, and it worked. Industry spent a like amount, more than $100 billion, to improve the wastewater treatment in cities and industries, and it worked. But we had a national will, a national resolve, and it cost money. I think we're going to have to do the same kind of thing if we really want water quality to improve in the future, and there will be benefits for flooding and runoff as well. But we're going to have to, I think, come together with the agricultural community, figure out how to do this thing most cost effectively, and resolve to invest in the kind of changes necessary for a better water quality. Thanks very much.